Page 260, Linear Regression using Microsoft Excel. Linear regression is part of the daily regimen of most technologists. In previous lessons, we performed linear regression using the Sharp scientific calculator and Excel. For nonlinear data such as semilog and inverse and power and exponential data, we performed linear regression after linearizing the data by some mathematical transformation. Recall we also performed a regression on quadratic data using the Sharp calculator, but only to a very limited extent with Excel. Now in this unit, let's scroll to the next page, that we will study more tools for performing regression and will extend its application to include examples such as, and let's scroll down the list here, calculating the uncertainty of forecasted X concentration values, calculating the margin of error and confidence limits for a forecasted value, determining the limit of detection from a calibration curve, and time permitting, we'll probably get to an example of multiple linear regression. Let's go to page 262. When using instrumental methods of analysis, it is often necessary to carry out a calibration procedure by using a series of samples of known concentrations of the analyte. These are our standards. A calibration curve is constructed by measuring the instrument signal for each standard and plotting this against concentration. Now our convention is to plot the dependent variable, that is the measured signal, on the y-axis, and the independent variable, usually the concentration, on the x-axis. Provided the same experimental conditions are used for the measurement of standards and the unknown samples, the concentration of the samples may be determined from the calibration curve by a graphical interpretation. Not all instrument responses are linear. Some are curved, but reproducible, and thus they're still useful. We will deal with linear calibration curves first. There's a bit of a misnomer here. Even though they are linear, that is straight, they are still referred to as calibration curves. Now all measurements have a degree of uncertainty, and so will the plotted linear calibration curve. Historically, graphing has been done intuitively, simply by eyeballing the best straight line by placing a ruler through the points in such a way as to give the best fit to all points. But with the advent of handheld calculators and computer graphing programs such as Excel, it's a simple task to apply statistics to define the most probable linear fit to the data with minimum error. The arithmetic equation of a straight line is given by y equals mx plus b, where m is the slope and b is the y-intercept. But in statistics, the linear regression equation is often written as y equals bx plus a. In this diagram, that's the convention that is being used, but we'll switch between the two forms whenever it is convenient. The method of linear least squares is used to determine the line of best fit. For each measured value of y, that is each instrument response, the distance between that y value and y hat or y prime, that's the corresponding y value on the regression line, is calculated. That's called a residual. Then y minus y hat is squared, and this is summed up for each point. And the line that gives the least sum of the squares of the differences is the line of best fit. Some of the equations used to do the regression calculations will be presented, but the derivation of these equations will be deferred to statistics courses, and the calculations will be performed automatically using various functions in MS Excel. The most common form of linear regression uses the Pearson correlation coefficient R, that's shown here, and this is used to assess the linearity of the data. The value of R will lie between -1 and +1. The nearer it is to +1, in the case of a positive correlation, or the closer it is to -1 in the case of a negative correlation, then the greater the probability that a definite linear relationship exists between the variables x and y. Now in the lab, we more commonly use the square of r, which is called r squared. And as a rule of thumb, for established analytical methods, a student with good technique should ideally obtain an r squared of greater than or equal to 4 nines, decimal 9999. Now the beginning student with unpolished technique should obtain an r squared of no less than 0.995. The method of calculating r is based on 3 important fundamental assumptions that we need to be aware of. First of all, the x values are correct, meaning you prepared your standards accurately, and only random errors affect y. Secondly, the random errors of y are normally distributed. It fits a normal distribution. And thirdly, the random errors of y are not dependent upon or affected by the values of x. In other words, as the concentration increases, the random error should stay the same. Hence, the Pearson correlation method is called an unweighted regression. The Residuals Plot, which we'll look at very soon, is a tool that checks the appropriateness of Pearson's unweighted regression method. Page 265. There are many equations to be solved to do regression, and you will find these equations are presented in various forms that give the same result. The regression equations used in this example are shown below and in the worksheets on Blackboard. We'll go into them in more detail as we need to, but just in a general sense, let me mention that when you see in a stats formula a single s, like here, that would imply a sum or perhaps a standard deviation, whereas SS typically means a sum of squares, as you see here. We will deal with each of these equations as we encounter them in the various examples. A useful regression tool that is easily generated by Excel is called a Residual Output or Residuals Plot, and there are 3 examples shown here. In a Residuals Plot, the residuals, that is y minus y prime, for each sample is plotted on the y-axis and the concentration on the x-axis. So for example, these concentrations might be 0, 0.1, 0.2, up to 0.5 ppm, and the values on the y-axis represent the difference between y hat and y prime for each of the samples measured. The central horizontal line shows a residual error of 0. If all the measurements fell perfectly on the linear regression line, then all the residues would be 0. In reality, this will never happen, but in a good analysis, we'll see a random scattering of residuals that lie close to the 0 line. Now, other patterns, like we see here, may indicate a problem. So in example A, we see an unweighted linear regression model is appropriate. But in example B, we see that the residual errors keep increasing with the concentration. And that would suggest that a weighted straight line regression is more appropriate. In example number C, notice the curvature. The residuals fall below the 0 line, then above, and then below again. And this would suggest that a straight line model is not appropriate. Perhaps a quadratic model might give a better fit. So we'll move next to an Excel spreadsheet where we can do some linear regression. This Excel file is entitled Regression, and the worksheet is linreg. And on this worksheet we have 6 standard solutions of manganese plus 7, ranging from 0 to 25 ppm in 5 ppm increments. We have the corresponding absorbances of those standard solutions measured on a visible spectrophotometer. We also have absorbances of 3 samples of steel. We're measuring manganese and steel. The samples are digested and the absorbance of the solution is measured at the same wavelength as the standards. Using this data, we want to perform linear regression on the standards and then forecast the concentrations of manganese in the steel samples. A good way to start is plotting a graph of absorbance versus concentration and fitting a linear trend line to it. So we simply select the x and y values together of the standards, that is the knowns, insert, we'll choose a scatter plot with points only. On the Chart Design tab, I'll choose Quick Layout, number 1, to give us placeholders. This will be absorbance on the y-axis and concentration on the x-axis. And we'll call this manganese in steel. Standard curve. We'll get rid of the series legend title since there's only one data set. So right-click on any of the points, add a trend line, choose a linear trend line, display the equation on the chart, display the r-squared value. Alright, so what do we see? The r-squared is 0.9989, that's decent. I'm just going to move this out of the way. It certainly is linear, so linear regression is appropriate. So we want to calculate the concentration of the standards and the unknowns. To do that, we need the regression equation. Now we've done this many times already, so I won't take the time to type it in front of you. You know that you get the slope by using equals the slope function and enter the values as prompted. The known y's and the known x's. Our slope is 0.402. Likewise for the intercept, enter the known y's and known x's. Our intercept is negative 0.0029, and the RSQ is done in like fashion. So to forecast x values, we'll write the equation equals bracket. The y value is our first standard absorbance, relative reference, minus the intercept. This value, we need an absolute reference, hit F4, close the bracket, divided by the slope, this value here, absolute reference, and enter. We're predicting 0.7 for a value of 0.00. Well, let's drag that down to the bottom of the standards and take a look. Some of these look very close. Some look not so close. Let's calculate the percentage error. That'll be equal to bracket measured minus the true. The order doesn't really matter here, but here's our measured value minus our true value divided by the true value times 100%. As expected, we get an error division by 0 because our true value is 0, but no problem. Let's calculate the other values. Let's reduce those decimals. So what do we see here? So we're plus 0.9%. That's very good for the first standard. The next two standards not so good. Negative 5%, plus 3%. 3% is acceptable but not great. And the last two are very good. So certainly towards the bottom and the top of the calibration range we could expect good data. Let's go ahead and get our unknowns as well at the same time. So here are our forecasted concentration for our unknowns. To evaluate their accuracy, we want to look at the standards of similar concentration or similar absorbance ranges. So 0.1 is in the range of 0 to 0.2, and it's maybe okay. We can't calculate the 0 value, but at the high end we're probably pretty good. The error is small. In the middle of the range, like 0.5 sits in here, we can expect some significant error. We'll deal more with error calculations later in this unit. Now we don't technically need to calculate the y prime values, but I want to do it in this case to show you how this information is used for regression purposes. So let's go ahead and get the y prime values. We write the equation y equals a plus bx. That'll be equal to a, which is the intercept, f4 for absolute reference, plus the slope, b, f4, times the value of x, that's our known x. F14, relative reference, is 0.00, so that predicts well. Let's autofill to get the absorbances forecasted, the y prime values for all the other standards. Next we want what's called a residual. The residual is the difference between the y value measured and the y value forecast. A simple subtraction equals the y value observed minus the y value forecasted. Now we want to square these residuals. That'll simply be equal to the value in column I raised to the second power, and drag those down. Now I've put in here an AutoSum function. This value, the sum of the squares of the residuals, is used to calculate an important statistic called the standard error of the regression, symbolized in a variety of ways on different statistical books and websites. S-res, S-y, standard error of the y values, the standard uncertainty of the regression, and it's calculated as the root of the sum of the squares of the regression, this term here, the root of it, divided by the number of degrees of freedom, and that will be number of calibration points minus 2. So right here, there's a function for this in Excel. It's equal to STEYX. Let's do that. Equals STE. There it is, YX. So tab, and just follow the prompts. The known y's are here, comma, known x's are here, close bracket. There's the standard error of the regression, 0.139. This is used to calculate the standard uncertainty of a forecasted value, a forecasted concentration value, as you will see. Now these four important statistics, the slope, intercept, RSQ, and standard error, or standard uncertainty, can be generated using a single Excel function called LINEST. LINEST stands for linear estimate, which reminds us it only works for linear relationships. So don't be applying it to curved quadratics, polynomials, only for linear data. To use this function, select these cells. I have a total of 5 rows and 2 columns. This is the maximum amount of data you can get from LINEST. You select them in advance, and you can type a function in, but let's go to the insert function dialog box as a guide here. If you want to find the function, you could type up here LINEST, and it'll highlight it for you and say OK. And just follow the prompts. The known y's are for the standards. The known x's for the standards. Now the constant. This dialog box says constant is a logical value. The constant b, which is the slope, is calculated normally if constant is true. We do want the value of the slope calculated, so make sure that either you put a 1 in here, which implies true, or omitted is the same thing. And finally, the stats function. Stats is a logical value. It returns additional regression statistics if the value is true. We do want those additional regression statistics, so hit 1, but do not press enter. Do not click OK. Whenever you want Excel to generate multiple values from a single function, always hold down the Control-Shift key. With the Control-Shift key held down, press and release the Enter button, and you'll get all the values. If you only got one value, it's probably because you released the Control-Shift key before you released the Enter key. So just, if that happens, press F2, which is Edit, and just repeat it. You'll get it. However, I noticed that with the latest version of Office 2016, Excel will generate multiple values simply by clicking OK. So here's what Excel has given us. We're given the slope, same as we get from our slope function. The intercept, likewise the same. So what values does LINEST give us? We see the slope, same as we got from the slope function, and intercept, same as from the intercept function. Now notice here that I've interchanged the notation, as is so commonly done in statistics. The equation of a straight line is y is equal to bx plus a. It's also mx plus b. So if there's any confusion, just always check your regression plot and you'll see which value is the slope and which is the intercept. Also, we see the r-squared value, same as we got from the RSQ function, and the standard uncertainty of the regression. There's some additional values printed here. We have the sum of the squares of the regression and the sum of the squares of the residual. Well, the sum of the squares of the residual we saw is obtained up here and used in the calculation of the standard error of the regression. A direct application for these two values is not common in the analytical lab. And also we have the standard uncertainty of the slope, 00067, and the standard uncertainty of the intercept, 0101. These are occasionally used, as for example in determining the uncertainty in the standard addition method, which is in the notes, or perhaps in the method detection limit, which we'll look at later in this lesson. There's another tool in Excel that gives us these regression statistics and more, actually more than what we need. It's called Regression Tool. So if you slide over to the right, I'm going to click on the cell L11, Summary Output, where I want this to print. On the Data tab, choose the Data Analysis tool group and find Regression and say OK. Much like using the FStat tool or the TStat tool, so we want to enter in the values as prompted. So enter the Y values and then let's include the label, absorbance. Likewise for the X values, let's include all the X values of the standards and the label. Make sure label is selected. The 95% confidence level is chosen by default. That's what we want. For the output range, choose a cell which is in the top left corner. I'm going to choose cell L11 in my case. And check off residuals, standardized residuals, and residuals plots. The line fit plot, you could check it off if you want, but it just produces a graph. But we've already created a line fit plot and added a trend line to it, so we don't need this. Do not check normal probability plots and say OK. Overwrite, that's all right. Go ahead and overwrite. All right, so here's the regression statistics output. Now let me tidy this up and then we'll talk about it. So what do we see here? A lot of the same values generated by Linest and some more. So here is our R-squared value, 0.9989. Multiple R is the Pearson correlation coefficient, just the R value. The adjusted R-squared is something we will use in a later application. Here's the standard error of the regression, 00139. In this section down below ANOVA, we have the regression residuals, the sum of the squares of the residuals, same as we get here from Linest, and the residual sum of the squares of the residuals, likewise. The data to the right here is used to determine if there is in fact a relationship between X and Y. This has applications in, say, business or in broad technology. We're trying to establish if in fact X affects Y or Y affects X. This is not even a question in our applications. We wouldn't be doing analysis unless there was a very strong relationship between absorbance and concentration. So it really has no specific application. I'll mention it briefly. An F-stat is calculated. Notice it's very high, and a probability value. Now, the null hypothesis for regression is that there is no relationship between X and Y. The significance that's determined here is 4.5 times 10 to the minus 7, which is essentially 0. Therefore, we would reject the null hypothesis and say that yes, there is a very strong relationship between X and Y, but we knew this or we wouldn't be doing it in the first place. So really this section of ANOVA is of little to no value to us in our applications, and generally I would ask students not to report this in their lab reports unless they plan to explain the function of each term. And I have some of this earlier in the notes explaining what each term means, but again, it has no direct application for us, so best to just eliminate the ANOVA section. Here is the intercept. This is the slope of the relationship. Here are the standard errors as we determined down here as well. 00067, 0101, these are the same values. And again, a t-stat, probability values. Here again, the null hypothesis is being evaluated. We have no direct use for this. And these upper and lower 95% confidence limits, Technically, they could be used to calculate uncertainties, but they tend to overestimate the uncertainty of a forecast, and there is actually a better way to do this, which I will show you very shortly. So again, we don't really need anything from this section. The residual output is of use. Here are the 6 observations, the predicted absorbances, the same as we calculated here. Here are the residuals, y minus y prime. For each absorbance measured, we have the same values here. This is the residual divided by the standard deviation of the residuals. It's called standard residuals. The standard residuals give us an indication of the relative deviation of the points. Obviously, the highest standard residuals would be those points that are farthest from the line of best fit. The residuals plot, which we checked off, here it is. So here we have the concentrations of our standards, 0 to 25, and for each, this value here is a residual that's calculated here. And so if all our points fit perfectly to a straight line, then all of these residuals would be 0 and it would be a perfect fit. In reality, there should be some scatter, and the scatter should be random, being both positive and negative, and hopefully all the points lie fairly close to this 0 residual line. To finish this up, what we should do is right-click on it and change the chart type, and we'll change it to scatter with straight lines and markers. The straight lines give an easy indication of which points are farthest from the regression line and which are closest. So that's a residual plot. We could have done that ourselves right here. We could simply have plotted our residuals on a graph versus concentration. I'll do it quickly with you here. So just take concentration values and take the residual values, and we'll go insert a function. I'll have points joined by straight lines, and there's our residuals plot. Now this chart is one that I have already added axis titles and chart title to it. The one you get from Excel will not have that, but you know how to do that. Simply select the chart and go to quick layout number 1, and you have placeholders, and you can add those pieces as needed. I'll get rid of this one. So these are some important tools for performing linear regression in Excel. Page 278. So we've seen how to forecast the concentration of an unknown sample using the regression coefficients of a linear calibration curve. And then we could say, for example, that the concentration of our analate is 17 ppm. But that's not good enough. We have to be able to say 17 plus or minus a certain quantity at a certain confidence level. For example, the 95% confidence level. How do we do that? We need to know how to forecast the uncertainty of our concentration values from the regression line. And that's what this lesson is about. Take a look at this graph. I borrowed this data from Skoog. This is a calibration curve for isooctane, analyzed by gas chromatography. He has 5 standards of known concentration, and then these are the peak areas, the instrument responses. Here are the forecasted concentrations of the standards. And here's the equation of the line of best fit. Y is equal to 2.093x plus 0.2567 as the intercept. And as R squared is, well, it's okay. It's 0.99 at best. Now as we look at this graph, the dotted central line is a linear regression line of best fit. So the upper red line is calculated as y is equal to mx plus b, but we've added the uncertainty of the slope and the intercept. And the lower red line is calculated using y equals mx plus b, but in this case we're subtracting the uncertainty of the slope and the uncertainty of the intercept. Specifically in this example, it would be 2.093 plus or minus this uncertainty of the slope times x plus this intercept plus or minus the uncertainty of the intercept. Now where do the uncertainties come from? Well, LINEST and the regression tool in Analysis Tool Pack give us those values of uncertainty of slope and intercept. Now these upper and lower red lines, they represent the maximum uncertainty. They're not the most probable. Take a look at the graph. These inner blue lines, they are the most probable uncertainty at the 68% confidence level. And the combined standard uncertainty of the concentration would be the most probable, and it is calculated by the propagation of errors formula at the bottom of the page, or the one shown right below here. We're going to go to the bottom of the page first and talk about that, and then we'll come back and look at this alternate calculation. And so to calculate the most probable uncertainty, or the standard uncertainty, at the 68% confidence level for a forecasted value of x, here's the formula we would use. Y plus or minus the uncertainty of y, which also is obtained by Linus, that's your UR, the standard error of the regression, is equal to m plus or minus the standard uncertainty of the slope times x plus b, the intercept, plus or minus its standard uncertainty. But these have to be combined in the manner of the propagation of error formulas that we have looked at in previous courses in the program. So I rearrange the formula to solve for x, and so x is equal to the numerator divided by the denominator term. Now go to the propagation of error formulas. Recall that when we have values that are being multiplied or divided, the relative uncertainty of the concentration divided by the concentration or the result is equal to the root of the sum of the squares of the relative uncertainties of the terms. That would be the numerator is one term, and there's a denominator. So that's what's put here, the root of the sum of the squares of the numerator and the denominator, their relative uncertainties. Now within the numerator, you see we also have a term that's subtracted. And for addition and subtraction, recall the rules for propagation of uncertainty. The uncertainty of values that are added or subtracted is equal to the root of the sum of the squares of the absolute uncertainties. And so here we substitute in the root of the sum of the squares of the absolute uncertainties. And all of these values are obtained from Linus. We can then calculate the standard uncertainty of the concentration that we forecasted. This is a good calculation. The only difficulty is it's very tedious to type into Excel, but there is an alternate formula for calculating the standard uncertainty of the forecasted concentration. It gives similar, although maybe not exactly the same values, and it's a lot easier to type into Excel. And don't be worried by the fact that I say it's not exact and similar, because none of these are exact. They're all estimates. So we can't say that one's necessarily better than the other. They're both good estimates. Back at the top of the page, we'll look at the alternate formula that most authors use. So this is the formula that is most commonly used to calculate the standard uncertainty of a forecasted concentration from a regression line. Look at the terms with me. This is the standard error of the regression, UR, given by Linus, divided by the slope, times the root of these terms added together, 1 over k. Now k is the number of replicate y values, or instrument responses. If you run your unknown sample in replicates, k would be more than 1. If you only run one replicate, well then it's just 1. 1 over n. N is the number of calibration points of the calibration line. Be careful not to confuse this with the value of k. Normally we use n to represent the number of samples, but in this application n is the number of calibration points. Plus this term. We have y sub I, that will be the instrument response for the sample for which you're estimating the uncertainty of the concentration. Now if you did replicates, this would be the average value of the instrument responses. If it's a singular sample, then it's a singular response. Y bar is the average of your standards. The instrument response is the y values of the standards. That difference is squared, divided by the slope squared, and divided by the sum of the squares of the differences between all of the individual concentration of the standards minus the average concentration of the standards squared. Looks a bit foreboding. Some of this is simpler than it might look. Just a reminder here, U sub R is the standard error of the regression. So either of the two calculations just shown will give us the standard uncertainty of the forecasted value of the concentration. And that would be added or subtracted to the forecasted X concentration values to give us the 68% confidence limit of the mean concentration. Ultimately, we want to report the 95% confidence limit on our uncertainties, and so we simply multiply our standard uncertainty by an appropriate t value before adding and subtracting from the forecasted x prime values. We do not divide by the root of n. Root of n has already been included in the calculation of the uncertainty here, and therefore this UCX value is actually not just the standard deviation, but rather it's the standard error of the population mean of the uncertainty, because it's already been divided by root of n. So to convert to the 95% confidence limits of the uncertainty, all we need to do is multiply by the appropriate t value. And we'll go through this next. Now the worked example is shown in the notes, but it's also in Excel. Let's go to Excel and work through it there. So this file is entitled Regression. The worksheet is entitled Error Analysis. This data was collected by a student January 2020. She was measuring iron in potable water used by local breweries to brew beer. And we expected low levels, and so we used a colorimetric method using orthophenanthroline that measures low levels of iron with good precision. She had prepared 5 standards, 1 through 5, and she had to drop the third one, which appeared to be an outlier. So we have then 4 standards plus the reagent blank. Now the reagent blank is one of the standards. It's the zero concentration standard. The reagent blank contains the solvent, which in this case was water, plus any color developing reagents, and it gave an absorbance of 0.02. Many students think they should subtract the absorbance of the reagent blank from the standards. That is not correct, and I'll explain why later. So including the reagent blank as a zero concentration standard, we now have 5 calibration points. She forecasted the concentrations of her standards and percent errors and found those are quite low, so she got good recovery having dropped the third point. Here's the graph of her calibration curve. Here's the regression equation of the standards, and she has a very good r-squared 0.9995, which is reflected by the fact that we see very low percentage errors on the forecasts of her concentrations of the knowns. Linest was applied to the data, known y's and known x's, and we have 3 rows of data. That's actually all we need. It gives us the slope and the intercept, the standard uncertainty of the slope and standard uncertainty of the intercept, which we will not use. We have the r-squared 0.9995, and we have the standard error of the regression, which we will use. The layout shown here works very well for calculating standard uncertainties, and I would encourage you to try this and adopt it. Once the formulas have been built into the first column, they can simply be dragged or automatically propagated into subsequent columns so that each calculation is very simple with minimal changes required. So let's go through this. In this case, she had 3 water samples supplied by the breweries. Before we continue, I want to point out to you something that you'll likely notice in any case. The absorbances of the third sample are all higher than the absorbance of the highest standard, and this is incorrect. The student should have diluted the sample so that it fell within the calibration range of the standards. As it is, it can't be reported to the customer, but we can still use the result to show the calculation of standard uncertainty from a forecasted concentration. So we'll leave it as it is for this lesson. She analyzed each sample for iron 3 separate times. This then is the average of the 3 absorbances. She then forecasted the concentration of each of the samples using the equation x is equal to y minus the intercept divided by the slope. Y is the particular absorbance. The intercept is obtained here, absolute reference to cell D20, which is obtained from Linest, divided by the slope, absolute reference to C20, again obtained from Linest, right here, C20. Once you have that, you can simply drag that across for all 3 samples, and you can drag it down as well to obtain concentration readings for all of your replicate analysis. You should not just calculate the concentration based on the average absorbance. It can be done, but then it doesn't allow you to calculate a standard deviation on your replicates, and you do want to see that. So after you have 3 concentrations calculated, you can calculate an average for sure, but then calculate the standard deviation of your replicate concentrations, 0.01, and then the relative standard deviation, CV. You can see what these are. Now we can evaluate them. So they should be less than 2% ideally for instrument analysis. And you see in this case, she has values that are less than 2%, only 1%, and this one's a little bit high, but it's acceptable. So by doing individual concentration calculations, we are able to calculate the standard deviation of our forecasts as well as the CV. The next step is then to calculate the uncertainties, and that follows here in what's called the error analysis. So I believe this layout is about as easy as we can make it for the calculation of the standard deviation of the forecasted concentration in this cell. But let's come down from the top and take a look. I have the sample name and then the average concentration, which is just copied from above, in this case from G10. We want next the standard error of the regression, which is right here from Linest, UR. Now, the standard error should be included with absolute references. That same standard error applies to all calculations for all samples. Rather than dragging this formula across, an easier way to handle this is to type the formula equals cell G16 in the cell H16. And in the next cell beside it and to the right, type equals H16. That way, when you enter the value for the standard error of the regression, these will automatically populate. You don't even have to drag or autofill across. The slope is also obtained from Linest here in cell C20. And again, you can use absolute references and drag, but it would be easier simply to write equals G17 and then equals H17, and these will auto-populate for you. Next in the formula we need K. K is the number of replicates of samples. So you can do a count function if you wish to count the number of replicates here, or you can put it in by hand as you wish. It's just 3 in our case. The next term we need is N, the number of calibration points. In that case it's 5. And you can use a count function. You can count the values from B3 to B7, or you can count these values C3 to C7. It'll give you the same number. That's the number of calibration points. Next in our formula we need this numerator term. This is the absorbance of the replicates. It's the average in this case since we have more than one, and that's simply a reference to right here, cell G6. Now we want a relative reference here, and that can be dragged across to all the cells. So for the second sample it would read the absorbance in column H, and for the third sample in column I it will read the average absorbance of the replicates in column I, in cell I6. Next we need Y bar. And Y bar is simply the average of your standard Y values. So it'll be an absolute reference. This will not change. It's true for all samples. So once again, you could drag the formula or simply use equal signs to keep referring to the cell, so it'll automatically populate for you. We have the slope already, and the last term we need is the sum of the squares of the differences between the individual concentration values x sub I from the average concentration value of the standards, x bar. Now fortunately, Excel has a function that automatically calculates it for us, and it's called deviation squared. So here it is. It's simply equal to deviation squared, and just scroll over all the x values, B3 to B7, and it gives us that value. Simplifies this a great deal. So finally now we're ready to calculate the standard deviation of the forecasted concentration. And again, we'll be using this formula. Now, having laid it out as we have, look how easy this is to type in. I want to first just direct you to the sequence of the cell addresses. Note with me, G16, G17, G18, G19, G20, G21, G22, and then we refer back to the slope again, G17. So we just have to work our way down the column. Follow with me if you would. We have the standard error of the regression, which is right here in G16, divided by the absolute value of the slope. We don't need the absolute value because in calibration curves normally these are positively correlated, so if you needed to put the absolute value sign you could. We don't need it in our case. Typically we won't for calibration curves, and that's G17 right here, times the square root of the sum of a collection of terms, 1 over k. So here's k in G18. It's the number of replicates plus 1 over the number of calibration points, G19, which is listed here, plus here's G20. G20 was a reference to the sample replicate instrument response average, minus y bar for all the standards, and that's right here in G21. That is squared. Notice the term is squared in the numerator. Now I chose to divide by the deviation squared first, just to keep the numbers increasing sequentially. G17, 18, 19, 20, and 21, and so on. So here we're dividing by G22, which is the deviation squared term, and finally we're dividing by the slope squared. See it here, slope squared, G17 squared. And having done that, we have a standard deviation of our forecasted concentration of 0.01. To obtain the standard deviation of the other samples, simply drag the formula to the right. Because we use relative referencing for the average y value of the sample, then it'll automatically pick up the 0.182 instead of the 0.146. The only thing you would ever have to change is if you had a different number of replicates for a given sample. That's the only thing that would change in the formula. And you would just correct these up here as you go, and everything else is the same. Just drag and you have the answer immediately. Whenever you calculate a standard deviation, for sure you also want to calculate the coefficient of variance, which is the relative standard deviation, and that will be equal to the standard deviation divided by the sample average, which is up here, times 100%. Recall that for instrumental analysis we should be below 2%, and in fact these values are, so that looks quite good. Let's pause here. A question you should be asking yourself is, why did we calculate the standard deviation of each sample twice? We did it once from the replicates, and then we did it again from the calibration curve. Notice in the first sample it's pretty much the same. Likewise in the third sample, 01 and 01 is pretty much the same. For the second sample, the standard deviation from the replicates looks higher than from the calibration curve. So which one is correct? Which one do we report? Let's think about how each one is calculated. Calculating the standard deviation of the replicates does not consider the variation of the calibration standards. It assumes that r squared is 1, and clearly it isn't, and it pretty much never will be. On the other hand, calculating the standard deviation from the calibration curve does so without regard to the variation of the individual sample absorbances. We use the average absorbance in our calculations. So other than disregarding outliers, we assume that there's no variation in our individual samples when we use the calibration curve calculation of standard deviation. Now in regard to outliers, if you check this highest first point, 0.188 absorbance, both Grubb's test and the Q-test tell us that this data point should be included. It should not be disregarded. If the sample replicate absorbances are simply replicates from the same solution, then they're just the measure of the stability of the instrument, and they don't fairly include all of the variation in the method. But if these sample replicate absorbances are taken from different solutions, from different flasks, they indicate not only the instrument variation, but also the variation in sample preparation, probably involving pipetting, diluting, mixing, and perhaps even sample digestion if that was involved. If the calibration standards are prepared in similar fashion to the samples, then the standard deviations of both methods should be similar. If, on the other hand, the calibration standard preparation involves less workup than the samples, it would not be surprising if the standard deviation from the calibration curve was less than from the sample replicates. So how does that answer our question? What standard deviation should we report? Well, one approach would be to report the larger of the two standard deviations for a given sample. Another approach would be to say, well, each of these measures slightly different sources of variation, and perhaps we should combine them. So if you combine them, you don't simply add them together. The combination of uncertainties is done using the rules for propagation of uncertainties. Remember that when you are combining two uncertainties, the combined standard uncertainty is equal to the root of the sum of the squares of the individual uncertainties. So in the example, sample number 2, 0.01 squared plus 0.02 squared is 0.025. And the reason you simply don't add them is because uncertainties are positive and negative. When you combine them, there's always some cancellation. They don't simply add together. So that's a second approach you might think should be done. All of the authors from the analytical textbooks advise us to report the standard deviation from the calibration curve, assuming it's a better measure of the standard deviation of the entire method. So what do? Do we hide the second sample? Do we ignore it? Do we tell the boss? What we do is we look at it and say, what's happening here? It looks like the first replicate is somewhat higher than the second two. Perhaps the glassware wasn't as clean here. Probably what the student should do is run a couple more of these replicates to get a better measure on precision. So stats doesn't necessarily tell you why results are varying, but they give you a way to honestly and logically evaluate the data. And then it's up to the technologist to figure out the why and how to correct the errors and how to minimize the variation. For the purpose of this lesson, we'll use the standard deviation calculated from the calibration curve in reporting our results. At work, it may be up to you to decide the best approach to handling a disparity in the results of standard deviations by these different methods. And that may depend upon whether this analysis is being done for internal control within the corporation or whether the sample is being certified for shipment to a customer. So recall that the standard deviation, which in this case is actually the standard error of the mean, is at the 68% confidence level. To actually report a value, we want to report at the 95% confidence level, so we need to expand our uncertainty to that level. We do it by multiplying this S value, standard deviation, times a T value. To obtain the T value, we need to know the degrees of freedom. The degrees of freedom is the number of calibration points minus 2. Any two-variable linear regression has n minus 2 degrees of freedom. 5 minus 3 is 2. For the t value, you can look it up in a t-table or simply use the Excel function equals t plus or minus inv dot 2 for a two-tailed t-test at the 95% confidence limit, and these are the degrees of freedom. In this case would be 3, and our value is 3.18. So the 95% margin of error is t, the t value, which is G26, times the standard deviation, so it's 0.2. So then to obtain our 95% confidence limits, we simply add the margin of error to our concentration and subtract the margin of error from our concentration, and these then represent our 95% confidence limits on our forecast. So now that we know the margin of error, here's how we would report our result. We'd say the concentration of this unknown is 0.56 plus or minus our margin of error, 0.02, and that's ppm of iron, and CV equals 1%. Something like that tells us everything we need to know. We have a concentration which is reported with the same precision as our uncertainty. Uncertainty is in the second decimal place, so we report our result to the second decimal place, and we report our relative standard deviation. There's one other item on this spreadsheet that I want to direct your attention to, and this is the 99% limit of detection, or LOD, or simply detection limit, DL. They are the same thing. They're usually calculated at the 99% confidence level, and you really should calculate a detection limit every time you do a calibration curve. It doesn't cost anything. There are no extra samples to run. It's a simple calculation. Here's the calculation for the detection limit of the concentration. In this particular case, we were measuring very low levels of iron, so it's important to know that our concentrations were in fact above the detection limit. Otherwise, we couldn't report actual numbers. All we could say is below detection limit. In this case, our detection limit is less than our actual concentrations measured, so we can report the actual values. Here's how it's calculated. It's simply a t-value times the standard deviation of the reagent blank divided by the slope of the calibration curve. So you say, well, how do I get the standard deviation of the reagent blank? Well, if you think about it, the reagent blank is actually the y-intercept. Zero concentration, y-intercept. Well, that value is given to us right here. There's the intercept. There's the standard deviation of the y-intercept, 0018. So it would be simply a t-value times 0018 divided by the slope of the calibration curve. Now, most authors will go ahead and openly state that this value is in fact the standard deviation of the intercept or the reagent blank, but they virtually all will use the standard error of the regression equation, the standard error of y. And perhaps this is because it gives them a little bigger buffer to ensure that we can state with confidence that this is in fact the lower limit. Notice it'll make the lower limit a little larger. So it'll be a t-value times the standard deviation or standard error of the regression, the y-value, divided by the slope of the regression equation. Now for the t-value, you can look up in a t-table, but Excel of course has a function for it. It simply equals t.inv. 99% confidence level is 0.01 alpha value, and G25 refers to the degrees of freedom. And that is the degrees of freedom of the calibration curve because we're calculating it from that. Here's the calculation. Now, this particular test is a one-tailed t-test. We're not interested if we're above or below the detection limit. We're only looking at one side of the detection limit, so it's a one-tailed t-test. T.inv gives you a one-tailed t-test t-value. In this case, it's 4.54, so our calculation is simply G32, which is our t-value, times G16, which is the standard error of the regression, or of y, divided by the slope, up here G17, and we get a value of 0.05. Just before we leave this, there are a few more points I want to stress regarding the calculation of the standard deviation of a concentration forecasted. So to do that, we're going to go back to our course notes. Page 279. Be careful that for the analysis of errors from the calibration curve, K is the number of replicates of samples, but N is the number of calibration points. This is not the way we normally use the term N. I want to stress that you should always forecast the concentration of standards as well as your sample. Students have often asked me, why should I forecast the concentration of my knowns? What I want to know is forecast the concentration of the unknowns. Well, when you forecast the concentration of standards, it indicates the optimal level of precision that you can expect with your samples. This is your best case scenario. Samples are usually not quite as good as standards because they suffer from more sources of variation en route to the instrument. So at least find the best case scenario. Your sample forecasts will not be any better than your standard forecasts. Page 280. The limit of detection should always be calculated any time a calibration curve is run. There's no extra bench work required. Just use the data you already have from the calibration curve. Even if you're working well above the limit of detection, monitoring this value gives you information about the stability of the instrument and the standards over time. Now the LOD usually gives values that are very close to the MDL, the method detection limit, calculated by the EPA and the MESA protocol, which will be presented to you in a later course in the program and is shown in the notes subsequently. Now it's okay to show 2 sig figs for standard deviation on a spreadsheet, but remember to round this to 1 sig fig when you report a concentration to a client or a customer, and remember that the precision of the standard deviation, 1 sig fig, determines the precision of your result. Report your results in the following manner: concentration plus or minus the 95% margin of error, and then also report the coefficient of variance, typically in brackets. So for example, in our case we had 0.56 plus or minus 0.02 milligrams per liter of iron with a coefficient of variance of 1%. Recall that CV should be less than about 2% for most analytical analysis. And CV should also be reported to only 1 sig fig. Any more than this is simply baloney. It doesn't mean anything. Recall that standard deviation and relative standard deviation, they're not exact, they're just an estimate. Recall that in any measurement you are only allowed to report only one uncertain digit. So let's say, take an extreme case, if CV was 12%, well that would be terrible precision. Then who cares if it's 10 or 12? Just round to the nearest 1 sig fig, so you'd report 10%. Such a result would be highly uncertain. It would be meaningless to report 12% versus 10%. It's just way off. If, for some reason, you are asked to report standard deviation instead of CV and margin of error, then be sure to state the number of replicates. In the case of a calibration curve, this would be the letter K, so that the reader can calculate the coefficient of variance and margin of error. So for example, if you reported 0.56 plus or minus 0.01 standard deviation, and you told them that the replicates were 3, from this one can calculate the margin of error for a calibration curve as t times s, which would be 3.18, times the standard deviation of 0.1 plus or minus 0.2. You may be thinking, well, this should be 0.3, and yes, it would be the way it's reported. I reported it carrying all the sig figs that were in Excel, and this value was a bit smaller and it rounded down. But no bother, if it was plus or minus 0.3, it's a small difference in any case. The reader could then calculate the relative standard deviation by simply taking the standard deviation and dividing it by the value, multiplying by 100. In spectrophotometry, it is not uncommon that the absorbance of the reagent blank is higher than the solvent blank. Think about it. The solvent blank has the minimum in it, then you add color developing reagents and you may get some color. Perhaps there's a trace of your analyte in one of the color developing reagents. Often students will zero the instrument with the reagent blank, and this is incorrect. Analytical textbook authors explain that when possible, the absorbance of the solvent blank is used to zero the instrument, but the absorbance of the reagent blank is not. Instead, the reagent blank should be used as a zero concentration standard. If you look in the spreadsheet, that's exactly what we did. We used it as our lowest calibration point on the graph for zero concentration. This is particularly well suited to UV-Vis spectrophotometry, where color developing or complexing reagents are added. The reagent blank is the absorbance of the solvent plus the additional reagents without analyte present. I doubt that you'll believe this, but read the following quote from a renowned expert, one of many. This is from Miller and Miller, Statistics and Chemometrics for Analytical Chemistry. It is critically important to include the value of a blank sample in the calibration curve. The blank contains no deliberately added analyte, but contains the same solvent, the same reagents, etc. as the test samples, and is subjected to exactly the same sequence of analytical procedures. The instrument signal given by the blank will sometimes not be zero. This signal is subject to the same errors as other points on the calibration curve, so it is wrong in principle to subtract the blank value from other standard values before plotting the calibration curve. This is because, as shown in a previous chapter, when two quantities are subtracted, the error of the final result cannot be obtained by simple subtraction. That goes back to the propagation of errors and uncertainties. Subtracting the blank value from each of the other instrument signals before plotting the graph thus gives incorrect information on the errors in the calibration process. I rest my case. In other types of analysis, there may not be a reagent blank. For example, in FLAS, flame atomic absorption, you may directly aspirate a water sample into the flame without adding any additional reagents. In such a case, there is no reagent blank, and so you will not have a zero concentration standard, just zero the instrument with the solvent. Similarly, in GC and HPLC, there is likely no peak seen when no analyte is present, regardless of other reagents in the sample. And so again, there will be no reagent blank. In such cases, if you can add a point, 0, 0, to your calibration curve without damaging RSQ, then it is acceptable to do so. And that is it for this lesson on calculating the uncertainty of a forecasted concentration from a linear calibration curve.